morning everyone. This is Nirosha, and in this session I would like to teach about chemical kinetics. As this is a simple and short video, we will cover all the topics of chemical kinetics. And welcome to Spark Academy. So let's start the session. So our topic is chemical kinetics. So let's see what is chemical kinetics. So the study of rate of reactions and factors affecting it like temperature, pressure, catalyst and radiations is called chemical kinetics. So mainly this chemical kinetics describes about the rate of reaction. So what exactly meant by rate of reaction? So here rate is defined by change in the concentration, divided by time. So this gives the rate of the reaction. So this is mainly depends on temperature, pressure, catalyst and radiations. These are the external factors. So based on the rate of reactions, reactions can be of slow, moderate and very fast type. So they are classified in this three types. So very fast reactions. So example is precipitation of AgCl. How AgCl is precipitated in a solution. This is example of very fast reaction. And slow reactions, this is a general reaction, rusting of iron. And next, reactions take place at moderate speeds, neither fast nor slow, at moderate speed, that is hydrolysis of starch. So let's see what is meant by rate of reaction. See, rate of reaction is defined as the rate of change of concentration of a reactant or a product per unit time. As we have discussed in the first slide, rate is change in concentration by time. See, exactly change in the concentration gives divided by time gives rate of reaction. Here C denotes concentration and C2 denotes final concentration. C2 is final concentration and C1 denotes initial concentration. So the difference between the final concentration and initial concentration is given by C2 minus T1, and this T2 minus T1 is the final time. What is the end of the time taken at the end of the reaction, and T1 is the initial time at which the reaction is started. This gives T1. So the difference in the time is taken here, T2 by T2 minus T1. So this exactly gives the rate of reaction. Now let's see, rate of reaction decreases with time because concentration of the reactant also decreases. Obviously, if the concentration of the reaction decreases, rate of the reaction also decreases, because rate of the reaction is directly proportional to the concentration of the reaction. For example, if we see equation here, 2 moles of NO2 plus F2 gives rise to 2 moles of NO2F. Here NO2 is taken as 2 moles, F2 is taken as 1 mole. On the product it gives 2 moles of NO2F. So observe this, rate of reaction decreases with the time because concentration of the reactant also decreases. So let's see, here reactants are NO2 and F2. So there are 2 moles of NO2 and 1 mole of F2. So which will complete fast? F2 will complete fast. So this is in less quantity. So the rate of reaction depends mainly on F2 here. See, here it is given the rate of reaction is measured by the decrease in the concentration of F2. Got it? Which is in less quantity. This justifies the rate of the reaction. So as per the formula, what will be the units for the rate of the reaction? Concentration is given by formula number of moles by volume. So obviously number of moles unit will be moles for number of moles, and for volume it is liter, and what is for time? It is second, right? So it is second. So it is second. Completely it gives the unit for the rate of reaction is mole per liter per time, that is mole, liter inverse and time inverse. This gives the unit for the rate of reaction or atmosphere time inverse. Since if we take in terms of pressure, it will be atmosphere time inverse. Okay, now let's see average rate of reaction. What do you mean by average rate of reaction? It is by dividing the total change in the concentration of the reactant or a product by a time interval. By dividing the total change in the concentration of a reactant or a product by a time interval. Here we are taking change in the concentration of the reactant or a product. See, in this graph it is clearly shown. For suppose if I take a reaction, A plus B gives rise to C plus D. Here A plus B are called reactants and C plus D are called products. This average reaction is given by the change in the concentration of the reactants or by the products. So when a reaction takes place, the reactants, that is A plus B, will start reaction and they gradually get decreased. Reactants quantity will be decreased and finally they start forming the products. It means the quantity of the products will be increased. So finally the disappearance of the reactants and the appearance of the products takes place in a chemical reaction. So if we plot a graph between concentration and the time taken by the reactant, here observe the time taken by the reactant. So the average rate is given by change in the concentration of the reactant, see, minus delta of R represents change in the concentration of the reactant by time taken. Here this minus sign represents there will be decreasing in the concentration of A and B, decreasing in the concentration of the reactants, that is represented by this minus sign. And when we check for the products, it will be plus sign because the appearance of the products gradually increases. So it will be positive sign. Here the graph will be a curve, downward curve, and here for product, because the product's concentration is decreasing, it will be a downward curve for reactant. For product, the concentration of the products is increasing, so it will be a upward curve with a positive sign, positive slope. See, this is the rate. This plus sign denotes the concentration of the products will be increased. And if we observe A question: for the chemical reaction N2 gaseous plus 3H2 gaseous gives rise to 2 moles of NH3. This is the formation of ammonia. So what will be the correct option for this? So let us see, this is a chemical reaction. If we write a rate equation for this, how can we write a rate equation for this? Here there are 1 mole of nitrogen gas and here there are 3 moles of hydrogen gas. So if I write it in a differential form, the number of moles will become to the denominator and there will be the differential equation in this way. D, change in the concentration of N2 by dt. Since this is a reactant, it shows a negative sign. That is equal to the next, this is disappearance, so it is a negative sign since the stoichiometric coefficient is taken in a denominator. So this becomes minus 1 by 3 change in the concentration of hydrogen by dt, that is equal to appearance of the products, that is showing a positive sign, 1 by 2 of change in the concentration of NH3 by dt. So this is the rate equation. So which justifies the correct option here? See, option 1, 3 moles of, if we take this here, 3 moles of change in the concentration, so this is wrong because the stoichiometric coefficient should come in the denominator. For option 2, minus 1 by 3 dH2 by d2 is equal to, so here minus sign, we should not get minus sign in the product because the appearance of the products is shown by plus sign. What about this? Minus d of N2, concentration of N2 by dt is equal to, here stoichiometric coefficient is taken in numerator, so this is also wrong. And observe this option, fourth option. Yeah, this is showing these two equations. So the answer is fourth one. So let's go into the next question. For the reaction, same ammonia formation, if change in the concentration of NH3, the rate of NH3 formation is given as 2 into 10 to the power of minus 4 mole liter inverse and second inverse, the value of, what will be the value of change in the concentration of hydrogen would be. So by applying this rate equation, we can solve this question. See here, change in the concentration of NH3 by dt, this is given as, this term is given as 2 into 10 to the power of minus 4. So if we apply it here, dHT by dt, this is minus 1 by 3, that is equal to, that is equal to 1 by 2 change in the concentration of NH3 by dt. So we need to find the value of change in the concentration of dHT by dt. So what will be this? So let's see, apply it. If we put this value in this way, this 2 will be cancelled. This will be 10 to the power of this minus 4 liter inverse and second inverse. Let's see here, minus 1 by 3 ht by dt is equal to 1 by 2 into twice of 10 to the power of minus 4. So both will be cancelled. So what will be the value of dht by dt? That is equal to 3 into 10 to the power of minus 4 mole inverse and liter inverse. So answer is option D. So now let's see what is meant by specific rate reaction rate. For example, n moles of A is on reaction, it is forming a product. For this n moles of A, the rate of reaction is given by minus dx by dt. This gives change in the concentration by change in the time, gives rate of reaction, which is directly proportional to the concentration of A to the power of n. Concentration of A to the power of n. Or if we remove this proportionality, we will add a constant, that is k. This k is known as rate constant. That is rate constant. This gives the rate law of any equation. That is minus dx by dt is equal to k concentration of A to the power n. N is the number of moles of A taken in the reaction. See, this is known as rate law equation. So if concentration of A to the power of n is equal to 1, it means if the value of n will be 0, then this total term will be is equal to 1, right? Then the change in the concentration of time will be equal to the rate constant. That defines the specific rate value. If the concentration is equal to unity, then the rate constant is defined as the rate of the reaction. That is the definition of exactly specific rate of the reaction. And now if we see at concentration value of unity, rate of reaction is equal to the value of rate constant. That's what we have discussed. Rate constant K is directly proportional to temperature. This is directly proportional to temperature, which means if the rate constant value is high, it means the temperature is obviously high. Rate constant does not depend upon the presence of catalyst or nature of the reactant. It does not depend upon the presence of the catalyst or any external agent added to it, or on nature of the reactant. Rate constant does not depend upon pressure, volume or concentration. It only depends on temperature. And unit for the rate constant is represented as same. What will be the concentration term? Mole per liter, right? Mole per liter. And what will be the unit for time? That is second. Since it is in denominator, we are taking inverse. Mole, liter inverse and time inverse gives the unit for specific rate constant. Now let's see what are the factors affecting rate of the reaction. The factors are physical state of the reactants. So how the reactant is taken. If it is taken in gaseous state, the rate of reaction is high when compared to liquid state and compared to solid state. Because gaseous state, the molecules can move freely and they can collide very easily, and they can give the product very easily. So the rate of reaction in a gaseous state is more compared to the liquid state, which are loosely packed, and in solid state they are very closely packed, and it is little tough for the collisions to form. So the rate of reaction is slow in this solid state. So this is the decreasing order of rate of reaction. Let's see another term, that is concentration. Rate of reaction is directly proportional to the concentration, as we have seen here. Rate of the reaction is directly proportional to the concentration, which means If concentration increases, the rate of reaction also increases. We can say in this peak, here in this first peak, the concentration is less, and this peak, the concentration is more. It means there will be successful collisions. It means the molecules can collide very successfully, which results in the formation of products which can help in the reaction to complete fast. Let's see this. Increasing the concentration of the reactants in a solution increases the rate of reaction as there are more number of particles to react. Yes, right? Since concentration is increased, there are more number of particles to react. This increases the frequency of collision between the particles. So, more collisions takes place. So, rate of reaction is directly proportional to concentration. Now, let's see one more term, that is pressure. For gaseous reactants, for gases, let us take the reactant in a gaseous form. The rate of the reaction is directly proportional to pressure. Let's see. If we take a reactant in a container in this way, as the concentration increases, if we apply pressure on this reactants, the concentration of the reactants will be increased and there will be more successful collisions which results in formation of products. Increasing the pressure of the reaction involving gases forces the gas particles to come closer. Yeah, by applying pressure, these particles will come closer. This will increases the frequency of the particle collisions. Yes, as they come closer, the collisions will be more and therefore increases the rate of the reaction, which is directly proportional. Rate of reaction is directly proportional to pressure. And now another factor, that is radiation. For a photochemical reaction, the rate of reaction is directly proportional to the intensity of radiation. If the intensity of the radiation, external energy which we give to the reactants is more, then the rate of the reaction is also more. The rate of reaction for photochemical reactions depends upon the intensity of light radiations which we give. That is in a that they are called photochemical reactions, which means which involve the light radiations, and it increases the absorption of photons. So remember this, the rate of reaction is directly proportional to the intensity of radiation. And one more factor, important factor, increasing in the temperature of reactants. If the temperature of the reactants increases, there will be more number of collisions between the reactant molecules. So the rate of reaction is also very high. So if we see a graph plotted between percentage of room particles and this energy particles. So if it is at room temperature, the reaction is in a moderate way. If the temperature is raised for plus 20 degrees centigrade than the room temperature, there will be change in the graph. It means the reaction happens very fast. This is the whole reaction path. If we increase the temperature, the reaction will increase. It shows increasing the temperature increases the kinetic energy of the particles, which increases the movement between the reactant molecules. This increases the frequency of the particle collisions. So collisions will be increased, and a greater portion of collisions will have the sufficient energy required to react. Since there is more energy for the reactant molecules, the reactions will occur fast because of the increasing in the temperature. Next factor is surface area. In case of heterogeneous reactions, greater is the surface area, faster is the rate of reaction. If the surface area is more, then there will be more exposure of the surface to the for the reactant molecules to collide, so which is directly proportional to the rate of reaction. For example, coal dust burns fast than large coal piece. Coal piece is in this way. Coal dust, if we spread it on a paper, it will be as the size of the paper. It means it will have large surface area compared to the coal piece. So this will have more rate of reaction than this coal piece. So similarly, one more example, wood shavings burn fast than a log of wood. Obviously, because this wood shavings will have large surface area compared to the log of wood. Here it is shown in the picture, increasing in the surface area. It is, suppose if we take this as a log of wood and we take it as wood shavings, so they have large surface area compared to the log of wood. So there will be more successful collisions in this, which is having more surface area. Increasing surface area of solid reactants increases the number of particles that are exposed and avail particles for collision, thus increasing the rate of reaction. As a consequence, increases the frequency of collision, which is directly proportional to the rate of reaction. Yeah. Next, use of a catalyst in a reaction. So if we use catalyst in a reaction, obviously it will increase the rate of reaction, but there are some types in the catalyst. Let's see in detail. A catalyst provides an alternative route for the reaction with a lower activation energy. This means the particle collisions need less energy in order for the reaction to occur, thus increasing the rate of reaction. For example, here is A and here is B. If A need to reach B, then it regularly reaches in this way. Suppose A is the reactant and B is the product. For reaching to B, it regularly uses this way. If I add a catalyst to it, it will show a shortcut way to happen the reaction. So if I add a catalyst, here, if I add a catalyst here, it shows the shortcut way for the reaction to occur. So this lowers the activation energy, and this helps in fasting the process of the reaction. So let's see here, if we take a graph between the energy and reaction process, this EA is known as activation energy, the energy required for the completion of the reaction, for the reactants to become to the products. The energy required is called activation energy. So this red line denotes without catalyst. Without catalyst, it requires higher activation energy to convert into products. If we add catalyst, see this blue line, it will occur in a small pathway, lowers the activation energy and speed up the reaction. So there are two types of catalyst here, positive catalyst and negative catalyst. If we add a positive catalyst, which decreases the activation energy by shortening the path, this is the, if we add positive catalyst, the activation energy is decreased by shortening the path. This green line denotes positive catalyst, and another catalyst is the negative catalyst, which increases the activation energy of the reaction by enlarging the path of reaction. It means it makes the reaction slow. This positive catalyst increases the speed of the reaction, and negative catalyst decreases the speed of the reaction. So this is also one of the most important factor for the rate of the reaction. Now let's see types of reactions: elementary reaction and complex reaction. So what is meant by elementary reaction? Elementary reaction is nothing but a simple reaction, simple one-step reaction. The reaction which occurs in one step are known as elementary reactions. And what are complex reactions? In the name itself it is there, complex. It means there are many steps which are happening in a reaction. Such type of reactions are called complex reactions. In this complex reaction, each and every step are elementary reactions. Understand this? Elementary reaction is a single step reaction. Complex reactions are multiple step reactions, in that each and every step is an elementary reaction. So let's see, the reaction which occurs in one step is known as an elementary reaction, and when a sequence of such reactions provide us with the desired products, then these reactions are termed as complex reactions. A group of elementary reactions which help us with desired products, in a reaction, such type of reactions are called complex reactions. For example, in the complex reaction of an alkane, the final products are always carbon dioxide and water. However, during this reaction, a series of elementary reactions takes place. See, alkane, if we burn it in an air, it will give carbon dioxide and water. And thus, there are single step reactions and there are complex reactions also. And these complex reactions, they will result in the formation of alcohols, aldehydes and acids, which you will study in organic chemistry clearly. Just understand there are multiple steps present in this alkane combustion. Okay. Now let's see what is molecularity. What is molecularity? So, molecularity is the number of particles, atoms or ions that must collide with one or another simultaneously, which results in a chemical reaction. See, understand this? What is molecularity? Molecularity is the number of particles, ions or molecules that must collide with one another simultaneously. The reactant molecules which collide one another simultaneously, which results in a chemical reaction. So, that is called molecularity. It is a theoretical value. It means it has a particular number. It is theoretical value given by our theory. It is always a whole number. You know what is whole number? Yeah. It never determines the rate of reaction. It just shows how many molecules are collided with one another simultaneously. See, how many molecules are collided one another simultaneously. That is shown by this molecularity of the reaction. It never depends on external forces like temperature and pressure. It does not depend on temperature and pressure. And if we take in a multi-step reaction, molecularity is determined separately in each step. For example, it is, if we take this in a complex reaction, that is, in case of complex reactions, the reaction taking place in a number of steps, that is complex reaction, the slowest step is called rate determining step. It means which occurs slowly. That step is called rate determining step. For a complex reaction, there are multiple steps, right? In that, one of the step will be the rate determining step, which is the slowest step. Next, the overall molecularity of the complex reaction is equal to the molecularity of the slowest step. That is what here. Yeah. If molecularity of the reaction is 1, the reaction is called unimolecular. See, for example, if PCl5 on reaction gives PCl3 and chlorine gas, here only one molecule of PCl5 is taken, so it is unimolecular. If molecularity is 2, the reaction is called bimolecular. For example, here C12H22O11 sucrose molecule is taken. When this reacts with water, it gives glucose and fructose. Sucrose on hydrolysis gives glucose and fructose. Here, one molecule of sucrose and one molecule of water is taken. So, the molecularity is 2. If the molecularity is 3, then the reaction is called thermolecular. Since here, observe this reaction, 2 moles of FeCl3 and 1 mole of SnCl2 gives rise to 2 moles of FeCl2 and SnCl4. Here, 2 moles of FeCl3 and 1 mole of SnCl2 combinedly gives the molecularity as 3. Next, we see order of reaction. So, what do you mean by order of reaction? So, order of reaction is defined as the number of reactants which determine the rate of reaction. So, molecularity does not show rate of reaction, and this order shows which determine the rate of reaction, or alternatively it is the number of reactants whose molar concentration changes during the chemical reaction. Understand this? Whose molar concentration changes during the chemical reaction. Concentration will be differed in a chemical reaction. That gives the order of reaction. It can also be defined as the sum of exponents raised on active masses of the reactants in a rate law equation. As we have studied previous rate law equation, what is rate law equation? Change in the concentration of reactants to the time taken dt dx by dt is equal to k to the concentration of the reactant to the power of n. N means number of moles present in the reactant. For this, the rate law equation is, for example, if I have taken an equation in this way, Ma plus Nb gives rise to products. Here the rate is defined as we have discussed previously, rate is concentration of the reactants to the power of their number of moles. Here for A there are m number of moles, for B there are n number of moles. Here this gives the rate equation. For determining the order, we need to add these powers of the present in the rate equation. That is, order is equal to m plus n. Hence, order is m plus 1, m plus n. It is calculated experimentally. Molecularity is a theoretical value, but order is a experimental value. It is an experimental value. It may be 0, negative or a fraction. It may be 0, negative or a fraction, while molecularity is only a whole number. It determines the rate of reaction. This shows the rate of the reaction. Order of reaction depends upon temperature, pressure and concentration. This is one of the important point. Order of the reaction depends on temperature, pressure and concentration. Next, anything present in excess is not counted in the order of reaction, which are involved in the reactants for the reaction. Molar concentration changes during the chemical reaction, right? This change in the moles, only that depends on this change in the molar concentration terms. And next, order of any reaction is determined by slowest step of the reaction. Since the main changes occurs in the slowest step, the order of the reaction is determined only in the slowest step of the reaction. Now, see a question. Which one of the following statement for the order of a reaction is incorrect? So, first option is order is not influenced by stoichiometric coefficient of the reactants. Yes. Order of the reaction is the sum of the power to the concentration terms of the reactants to express the rate of the reaction. Yes. And order of the reaction is always a whole number. Check it once. Order can be determined by experiments only. Yes, it can be. It is the experimental value. And what about this third option? Order of the reaction is always the whole number. No. Order of the reaction may be 0, negative or a fraction. So the answer is 3. This is the incorrect statement about order of a reaction. Next, let's see how many types of reactions are there. If we take a zero order reaction, what is meant by a zero order reaction? So, in a zero order reaction, the concentration of the reactant to the power is taken as 0. If 0 is taken to the concentration of the power in a rate equation, then they are called zero order reactions. For example, the reactant A is giving rise to the products P. The change in the concentration dx by dt is equal to K to the concentration of A whole to the power of 0. That gives K, because this value is equal to 1. Since it is a zero order reaction, we are taking to the power as 0. Anything to the power 0 is 1. So, thus dx by dt, change in the concentration, is equal to the rate constant in a zero order reaction. On integrating it, we get x equal to k into t plus c. If this integral constant is taken as 0, then x is equal to k into t. That is, the rate equation of zero order is given by k is equal to x by t. Here, units of zero order reaction are, since the units of the concentration is mole per liter, and for time it is second inverse or time inverse, because it is in denominator, it is in inverse. So, for every order of the reaction, it is most important to remember the units. There will be some questions asking on the units of the rates of reaction. So, remember this. So, few examples for zero order reaction. For example, if we take photochemical reactions which involves light, and this, if there is H mu in its on an arrow mark of any reaction, they are called photochemical reactions. If H2 plus Cl2 in presence of light, it gives 2 moles of HCl. This is a zero order reaction, one of the example for zero order reaction. Here N2O gives rise to N2 plus half O2. This is also example for zero order reaction. And ammonia gives rise to nitrogen and hydrogen. And here also CH3, COCH3 plus I2. This is also example for zero order reaction. Here also 2 moles of HI gives rise to H2 plus I2. And iodination of acetone, enzyme catalyzed reactions, everything comes under zero order reactions. Okay, let's see here few graphs determining the rate constant K. A zero order reaction has a constant rate that is independent of the concentration of the reactions. A zero order, understand this? A zero order reaction has a constant rate. Constant rate. There is no change in the slope. It is constant rate that is independent on the concentration. Independent on the concentration. This is concentration. Y-axis there is concentration. On x-axis there is time given. So, independent of this concentration, the slope K, the rate constant, is shown in the form of a straight line, decreasing straight line. That gives the graph of the zero order reaction. And here, let's see half-life. What is meant by half-life? The time for the reaction in which half of the initial amount is left. If we take 100% of the reactant, the time taken for it to complete the 50% of the initial substance, that gives the half-life of the reaction. Here the T half is equal to concentration of A by 2K. Remember this. For every reaction, remember the rate equation and the half-life period. The half-life period graph is on y-axis, there is T half. On x-axis there is a concentration term. It is shown as a straight line from the origin. From the origin it is shown as a straight line. This gives the zero order reaction. For example, let's take a question. In a zero order reaction, for every 10 degrees centigrade rise of temperature, the rate is double. If the temperature is increased from 10 degrees to 100 degrees centigrade, the rate of reaction will become. Understand the question? In a zero order reaction, for every 10 degrees rise of temperature, for every 10 degrees rise of temperature, the rate is double. If the temperature is increased from 10 degrees centigrade to 100 degrees centigrade, calculate the rate of the reaction. If a question is asked in this way, it means if the temperature is rate is double, it will be in the form of formula, the rate is equal to 2 to the power of n times. 2 to the power of n times. So here the temperature, what is the temperature difference if the temperature is increased from 10 degrees centigrade to 100 degrees centigrade? So what is the temperature difference? 100 minus 10, it will be 90, right? So what happens here? The temperature is of 90 degrees. Here there is 10 degrees rise in temperature. It means there will be 10 degrees, only 1% of 10 here. So n is equal to n is equal to 1 here. So this is double. Here it is 90 times, 90 degrees centigrade. So the difference is 90 degrees. So it is 9 times of 10. It means n value will be 9. So to calculate the rate of reaction here, K will be 2 to the power of 9. This is equal to 512. 2 power 9 is 512. So if the temperature is increased from 10 degrees to 100 degrees centigrade, the rate of reaction will be 512 times. So now let's see. First order reactions. First order reactions. So what is first order reaction? Here the rate of reaction is determined by one concentration variable only. So since this is a first order reaction, the rate of the rate is determined by one concentration variable only. It depends upon only one concentration term of the reactant. So here let T be the change in the time period, K is the rate constant, AR or small a denotes initial amount of the reactant, and capital A or A minus X denotes amount left after time t. Suppose if we take a reaction which is from A to B, if the amount of A is A at time t is equal to 0, since there is no reaction happening, B is 0. At time equal to t seconds, A is converting into A minus X. That means X the part of the A is undergoing reaction. So it forms this is at t is equal to t. This is giving rise to the product B. So let's suppose this is the reaction happened. Here are the terms which are explaining this. So which gives the rate equation K is equal to 2.303 by T log of concentration, initial concentration to final concentration. This you will get through taking the integral equations. Just remember this formula. Remember this formula. Rate equation of first order reaction is 2.303 by T log of concentration, initial concentration by final concentration. That gives, if we take the graph in this way, the concentration, the logarithmic value of this change in the concentration is taken on y-axis and time is taken on x-axis. This gives a slope which is showing the rate constant. This minus sign increase denotes that there will be a decreasing in the slope. This intercept is log a. By applying all the integral formulas to this, we will get a final rate equation as this one. So, for example, these are the examples of first order reaction. H2O2 on heating gives rise to H2O and half mole of O2, and NH4NO2 gives rise to N2 and 2H2O. N2O5, 2 moles of N2O5 gives rise to 4 moles of NO2 and O2. SO2Cl2O on heating gives rise to SO2 and Cl2. C6H5N double bond NCl on reacting with water, it gives C6H5OH N2 and HCl. And all radioactive disintegration processes are examples of first order reactions. All radioactive reactions comes under first order reactions. Next, features of first order reaction. So this is the rate equation. So let's find the units for first order reaction. This is the rate constant of first order reaction. Here the concentration units are cancelled and remaining is time, which is in the denominator. So the units will be second inverse. Second inverse will be the unit of first order rate reaction. K does not depend on concentration units or change in the concentration. This value of rate constant does not depend on change in the concentration. T half does not. Let's see what is half-life period for this. A first order reaction is a reaction that proceeds at a rate that depends nearly on only one reactant concentration. Since it is a first order, we are taking the concentration of only one reactant. So the T half of first order reaction is 0.693 by K. Here the T half, the time required to complete the half for the reactant to reduce the half, to reduce it to half, that gives the half-life period. So here the T half does not depends upon the initial concentration. So since it is independent of concentration terms, it does not depends upon the initial concentration. It depends only on the rate constant. Since it is inversely proportional, it depends only on the rate constant value K. So by taking this rate law equation, by plotting the change in the concentration on y-axis and time taken on x-axis, there will be a inverse curve on this graph. If we take T half on x-axis and change in the concentration on T half on y-axis and change in the concentration of x-axis, the curve will be also reversed curve. It is in case of T half. Okay, this is all about first order reaction. Let's see a problem based on first order reaction. A first order reaction has a specific reaction rate of 10 to the power of -2 second inverse. So this is the value of K. K is equal to 10 to the power of -2 second inverse. How much time will it take for 20 grams of the reactant to reduce to 5 grams? 20 grams. Initial mass is 20 grams. Final mass is 5 grams. So what they are asking to find, how much time it will take. So to calculate this, we need to obviously take the rate equation, because there are rate constant, time and concentration terms involved in it, but here in the question it is asking about, it gave information about mass. Now let us see what will be the information, what will be the relation between concentration and mass. Concentration is given by number of moles by volume, right? What is number of moles? Weight by gram molecular weight by volume, that gives concentration. It means here concentration is directly proportional to weight of the reactant. Weight of reactant. So in place of concentration we can directly take the weight of the reactant molecules. So by applying this rate law equation, that is K is equal to 2.303 by T log of A naught by log A. So this is the rate law equation, right? Since these concentrations are directly proportional to the weight of the reactant molecule, we can take initial mass by final mass. So what is K now? K is equal to 2.3303 by T log of, what is initial mass? 20 grams by final mass 5 grams, right? So here what is the value of K given in the question? 10 to the power of minus 2 is equal to 2.303 by T log of 5 force 20, right? Force 20. So this is log 4, that on simplifying gives 10 to the power of minus 2 is equal to 2.303 by T 2 log 2. If you simplify all this term, you will get the answer as 138.6 seconds. Since they are asking to find this time, if we take this time to the right side and to this 10 power 2 to the denominator, so the equation will be T is equal to 2.303 by 10 to the power of minus 2 of log 2. If you solve all this, you will get the answer as 138.6 seconds. Now let's see second order reaction. Here the definition of first order reaction shows a first order reaction is a reaction that proceeds at the rate that depends only on one reactant concentration. Since here this depends only on one reactant concentration, it is first order reaction. If it depends on two reactant concentrations, or if we take the molecule as two molecules, then the rate of reaction depends on both the molecules. Such type of reactions are called second order reactions. For example, 2 moles of O3 gives rise to 3 moles of O2. Here there are 2 moles of O3, and here CH3COO C2H5 and NaOH. This gives CH3COO Na plus C2H5OH, and if this is also a second order reaction because this depends on this concentration of these two reactions, and 2 moles of Cl2O gives rise to 2 moles of Cl2 plus O2. This is also a second order reaction, and 2 moles of NO2 gives 2 moles of NO plus O2. Here also the rate of reaction depends on two molecules. So these are the examples of second order reaction. Let's see a second order reaction. It is a chemical reaction in which the rate of the reaction is determined by concentration of two chemical reactants, as discussed above. Two chemical reactants, it is called a second order reaction, or the square of the concentration of one chemical element. It means if we take O3 here, 2 moles of O3 here. It means 1 mole of O3 and another mole of O3. That is square of the concentration of one chemical reactant. It gives second order reaction. Here the rate equation is shown in this way. Rate equation K is equal to change in the final concentration, 1 by change in the final concentration minus 1 by change in the initial concentration by time taken. This gives the rate law of second order equation, and this T half gives the half-life time of second order reaction. Here let's see what are the units of second order reaction. T half units of second order reaction. K is equal to, here there is difference between the concentrations, so there will be obviously a concentration term involved in the numerator. That is 1 by concentration, mole per liter. That is on inverse it gives rise to liter per mole inverse, and this time gives second inverse. So the concentration is liter, mole inverse, time inverse. And units for half-life is 1 by the concentration term. T half is equal to 1 by K of the concentration term. That is T half is, units will be inverse of this initial concentration, that is concentration term. And what are the features of second order reaction? Here the unit is, we have talked earlier, and T half is directly proportional to 1 by A. Here we can see here T half is inversely proportional to the concentration. 1 by means which is inversely proportional. T half is inversely proportional to the concentration. When concentrations are same, K, the rate equation is given in this way. When the concentrations are same, K is equal to 1 by T x by A of A minus x, where x is the change in the concentration, in the time limit, and A is the initial concentration, A minus x is the final concentration. When concentrations are different, the equation is in this way. K is equal to 2.303 by T of A minus B log 10 B of A minus x. When this is for A concentration, when this is B, and this is A of B minus x, this is the final concentration of B, this is the final concentration of A, and the change in the unit of concentration changes the value of K here. Here observe this, the change in the unit of concentration changes the value of K because they both are directly proportional. And this graph, which shows the second order equation, here 1 by the concentration at time t is taken on y axis and time is taken on x axis. There will be a line which is passing in this way. Here the slope is equal to the rate constant K and the intercept is 1 by A naught. So this gives the graph of second order reaction. For T half, it is a straight line from the origin. T half is taken on y axis and 1 by A naught concentration is taken on x axis. Here slope gives a straight line from the origin. So these are the second order reactions, and let's discuss few more concepts, that is about the pseudo order reactions, about the collision theory, about the Arrhenius equation, and the problems based on all these terms in the next class. Okay, thank you for joining.